So we were discussing that this plowing force and size effect. So here we discuss there is a contact between cutting tool and workpiece material at three locations. The first one where actual material removal takes place, that is the cutting edge of the cutting tool. Then the chip, while moving across this rake face, comes in contact with cutting tool in a certain region. That region is called as chip tool interface. And third one, when tool has got slightly worn out, there is a contact between cutting tool surface and finished work surface, and that zone is called as work tool interface. Okay, now out of these three zones, the force acting on cutting tool on the cutting edge where actual material removal takes place, if you compare that force, if I consider that one as Fa with the force acting on rake face of the cutting tool in this chip tool interface and force acting on cutting tool in this second zone of work tool interface, if I combine force acting in those two zones, that force combinedly called as flowing force. Okay, so the first one that acts on the cutting edge, we considered that one component of the force, and additionally the force acting in chip tool interface and work tool interface, that force combinedly called as flowing force. Why we call it as flowing force? Because this flowing force doesn't take any action in actual material removal. The material removal will be done by this cutting edge, and that is cutting force. Okay, except that the force acting in this chip tool interface and work tool interface does not produce any actual material removal, and because of that one it is called as flowing force. Now if I compare the force acting in this cutting on this cutting edge, so there is force acting on cutting edge, that is one component, and another one is this flowing force. Okay, so those two togetherly going to constitute the total forces acting on the cutting tool. Now the force acting on this cutting edge and this flowing force, this magnitude is very small compared to this flowing force. Okay, so get the difference between those two. The force acting on cutting edge is very small, whereas this flowing force holds the maximum proportion of the total force acting on the cutting tool, and that is going to be a large one. Now this force acting on the cutting edge varies according to machining. When you increase or decrease the depth of cut, this force component acting on the cutting edge is going to increase or decrease. If you increase the depth of cut, this will increase. If you decrease the depth of cut, this will decrease. Whereas this flowing force component does not have any effect of this depth of cut, or this flowing force component almost remains constant during the metal cutting. Either you increase depth of cut or decrease depth of cut, this flowing force is going to remain constant, and that holds large proportion of the total forces acting on the cutting tool. So now what we are going to correlate, we are going to correlate a relationship between this T0, that is depth of cut, and the total forces acting on the cutting tool. So now what will happen if I increase depth of cut, the cutting force or forces acting on cutting edge is going to increase, by small amount, because itself is a small proportion of total forces, and second is the flowing force, and that holds a large proportion. So when you increase T0, there is small increase in the cutting force, flowing force is almost constant. If you decrease T0, this force acting on cutting edge will decrease, but again that is a small amount, so there would be a small decrease, but this flowing force is going to remain constant. So what will happen when you increase T0, the material removal rate will increase, and there will be either slight increase in the cutting forces because of this small increase, or it will remain constant, right? But when you decrease this T0, the material removal rate is going to decrease drastically, but this flowing force component is constant, and this small component of force acting on cutting edge will decrease. But if you compare the decrease in material removal rate with total force, this will not decrease considerably. So what will happen because of that one? When material removal rate is more, cutting forces are more, that is fine. But even when material removal rate is less because of decrease in depth of cut, cutting forces are still considerable. So in short, when you remove a large amount of material, cutting forces are more, and that is fine. But when you remove a small amount of material by decreasing depth of cut, still forces are large. So when you decrease this depth of cut, the cutting forces are expected to decrease, but instead of decrease in cutting force, the cutting forces increases in proportion to this depth of cut. And because of that one only, if you remember, in case of abrasive machining, we said that in abrasive machining the specific cutting energy is very large. Why specific cutting energy is very large? Because in abrasive machining you remove a very small amount of material by using that small abrasive, and because of that one material removal rate is less, but that flowing forces are considerable, and because of that one specific cutting energy increases. So this phenomena is called as size effect. When you decrease the depth of cut, the cutting force, instead of decreasing, it increases in terms of specific cutting energy. Actual force does not increase, either it will remain constant or decrease by small value. But you compare that specific cutting energy, the energy required to remove unit volume of material, that increases with decrease in depth of cut, and this phenomena is called as size effect. Any doubt, any query in this one? If you have any, let me know. Yes, anybody? Should I move to next slide? I need confirmation from you people so that I can proceed to the next slide.
Yes, sir.
Okay. Thank you, Mrutyunjay. Thank you, Akash. So that's concept is called as size effect. Okay. Now, even with this concept, you can explain that question. One question was asked to you, in case of abrasive machining, why that grinding wheels are rotated with highest speed? That answer you can relate with this size effect. Okay, try to relate. If you are able to do that, that's fine. If you find any difficulty, you can ask me later. Next, measuring cutting forces and power. Now we know the reasons of generating cutting forces, the nature of cutting forces, even why we need to measure those cutting forces. That importance is also known. Now, how to measure those cutting forces? To measure the cutting forces, there is a device that is used, and that device is called as a force transducer. If you are able to recall the concept of piezoelectric material, what happens in case of piezoelectric material? If this is a block of piezoelectric material, and if you apply a certain force on that one, you are compressing that one, or even you are applying tensile forces and you are expanding that material. What happens in case of piezoelectric material? Whenever, because of application of external force, if its dimension changes, there will be development of electrical potential. Because of change in dimension, resulting from the applied external force, there will be development of electric potential. And if you correlate this one between change in dimension and develop potential, you can measure the force. Okay. Now to apply this principle in case of these piezoelectric transducers or force transducers, what they do, they will use three rings that will be placed in three directions. One will be horizontal, vertical, and the third one will be perpendicular to those two. So that one will be in x direction, the second y direction, and third one in x direction. So in whichever direction, so this whole thing will be combined together, and one cutting tool will be mounted on that one. That will remove the material. So on this cutting tool, if there is a horizontal force, this horizontal transducer comes into picture, deformation occurs in that horizontal transducer, and you will get the voltage generated. If vertical force act on that cutting tool, this vertical transducer will respond to that one, and you will get voltage potential. Similarly, in the third direction, if force acts on it, this another transducer comes into picture, and you will get the potential difference. So in whichever direction force act on the cutting tool, there will be three rings placed in that device. Those three rings individually measure the force acting in those three directions, and that you will get the voltage developed. And that way you can measure all the forces acting on the cutting tool. That is the basic principle of the measurement of the cutting forces in case of force transducers. Next, there is one small numerical that you need to solve. What much time is there? Okay, let's solve this one quickly. Let me read out this statement. We will use this image right here itself and try to understand this numerical. So in an orthogonal cutting, so again it is orthogonal cutting, T0 is 0.13 mm. So uncut chip thickness is given. V is 120 meters per minute. So cutting speed is given, alpha 10 degrees, that is a rake angle. The width of cut is 6 millimeter. Now you should not get confused when it comes to this width of cut. Width of cut is something different. What is that width of cut? When chip forms, this is cutting tool. This is a depth of cut, and this chip is going to have certain width. That is nothing but the width of cut. So that width of cut is given 6 millimeter. it is observed that TC is 0.23. Chip thickness is also given. This T0 is uncut chip thickness, TC is chip thickness, that TC is 0.23. You can compare the difference between those two. Uncut is 0.13, whereas chip thickness is 0.23, so almost twice. Then FC, cutting force is given 500 Newton, thrust force FT is given 200 Newton, and what we need to do, calculate percentage of total energy. So if I consider E is the total energy involved in the material removal, what we need to find, percentage of total energy that goes into overcoming the friction at the interface. So we need to find frictional force, and that frictional force will be used to calculate proportion of or proportion of this total energy that is going to be consumed to overcome this friction. So for that one, we need to calculate frictional force first. Okay. So this is the given data. Now to calculate percentage of energy, we are going to use this relation. Total energy, we know how to calculate total energy. PM is equal to FC into V, cutting force into cutting speed. Okay. And friction energy is nothing but it is product of F is the frictional force and VC is the velocity of the chip. So when this chip is formed and it moving across this rake face, the velocity of chip with which it is moving is called a chip velocity divided by VC. The V cutting speed is different, and we know that the chip's dimensions are different than the uncut material, and because of that one, this VC is going to have different value. So that velocity of chip is nothing but the chip velocity denoted by VC. So if you take ratio of those two, you will get the percentage of energy that is involved in the friction. So now this is F into VC divided by FC into V. Now this relation changes into this one. How this changes? If you are able to remember this relation, V into T0 is equal to VC into TC. This is a mass continuity equation that we wrote while discussing the velocities in the cutting zone. This is before cutting and this is after cutting. V is the cutting velocity and T0 is the uncut chip thickness, whereas VC is the chip velocity and TC is the chip thickness. So this is before cutting and this is after cutting. We are going to equate those two because mass entering and leaving or before and after should remain constant. And from this relation, T0 by TC, we know that R is the chip thickness ratio or cutting ratio, and that is T0 by TC. So T0 by TC, when you replace with R, you will get VC is equal to V into R. So VC is equal to V into R, or R is equal to VC by V. So here is VC by V. So that is replaced by this R. So F into R divided by FC. Now let's calculate the R. R is equal to T0 by TC. T0 is 0.13, TC is 0.23. When you calculate that one, you will get 0.565. That is the chip thickness ratio or cutting ratio. Now to calculate frictional force, there is a relation F is equal to R sine beta. For this one, you need to use merchant circle. From merchant circle, you will get this relation F is equal to R sine beta. Now, this beta is unknown. R we can calculate because FC and FT is given. If you calculate resultant of those two, FC square plus ft square under root, you will get this r that we can calculate, but this beta is still unknown. And to calculate that beta, there is alternative relation, fc is equal to r cos beta minus alpha. Now this fc is known, that is given 500 newton. R, suppose that we have calculated 530 newton, 539 newton. Alpha is again known to us. Where is that rectangle? Alpha is equal to 10. Unknown is only beta. So when you put all these values in this equation, you will get beta 32 degrees. Now once that beta is calculated, put that beta in this friction force relation. So you will get F is equal to 286 Newton. So now you have got uh, from this relation, you have got F. Fc is known, that you have calculated now. Sorry, fc is given input, f you have calculated 286 newton, and r also you have calculated 0.565. And when you put all these things in this equation, you will get 0.32. And when you convert it into percentage, that is 32%. So out of total energy, 32% energy will be consumed to overcome the friction between tool and uh, chip interface, or energy spent at the chip tool interface, that is going to be 32%. Any doubt in this one? I have tried to explain each and every concept. Still, if you have any doubt, let me know. Okay, last point, friction in metal cutting. Now, before discussing this nature of friction in metal cutting, let me take you to the Amonton's laws of friction, or Coulomb's laws of friction. For that one, again, you need to remember engineering mechanics. Can any one of you tell me the, or any of the law? There are, I'm not able to recall the exact number of number of those statements, but there are certain laws that governs the friction. Can any one of you let me know any of the laws? Anyone? There are many statements, but if you are able to recall any of those statements, you can let me know. Mrityunjay, unmute yourself.
Yes, sir.
Can you tell me anyone?
So the friction experienced by the object
Hmm.
can be dependent upon the nature of the surface it is in contact with.
Very good. The first thing is nature of the surface. Very good. I will write the things: speed, area. Then fourth one is
Normal force.
normal force. Then anything else? Okay, these are the important one. So it is dependent of the nature. So whether it is metal, whether it is a plastic, or whether it is leather, that is going to decide the coefficient of friction, right? That's good. Second, speed. Suppose this is one surface and this is another surface, this is moving in this direction, this is moving in this direction. If I increase the speed, what will happen? The frictional force will increase, decrease, or remain constant. No idea? Okay, this frictional force is always independent of the speed of sliding. We know that when it is in stationary condition, uh, till the limiting friction, the friction value keeps on increasing, and after that, once two parts starts moving, that value drops slightly, but after that it remains constant. And as two parts in motion, this frictional force is going to be independent of the speed of slide. Similarly, it is independent of the area also. Very good. Somebody said that uh, coefficient of friction or coefficient of static friction. Okay, who's that? Shubham. Okay, the friction of moving object is proportional and perpendicular to the normal force. Very good. The friction experienced by object is independent of the nature, sorry, dependent of the nature. Okay, friction is independent of the area of contact. Okay, kinetic friction is independent of the velocity. Very good. So it is independent of area, and it is directly proportional to the normal. Means there is one force in this direction, one force in that direction. Those two forces are going to place those two parts in contact with each other. And magnitude, suppose it has got n, so the frictional force is directly proportional to this normal force. Okay, these are the laws of the friction. These were first coined by these Amantons, then verified by this column, and now we are using those laws. But when it comes to metal cutting, when it comes to metal cutting, all these laws of friction, Amantons and column defined laws, are not valid in case of metal cutting. So what happens in case of metal cutting? In metal cutting, the coefficient of friction between chip and tool vary considerably and affected by change in, either you are changing speed, either you are changing rake angle, or any of the input parameter. If you change those parameters, this coefficient of friction is going to change. It will either increase or decrease. So the laws of friction doesn't holds good in case of metal cutting. That is the scenario of friction in metal cutting.